So the central, repeat after me, the central limit theorem is sample mean, the distribution of the sample mean approaches the normal as the sample size gets large. Perfect. Got that? Did you?
Yeah.
Unbiasedness. It's a good thing you guys are really good people. Unbiasedness. Means that the sample mean is equal to the population mean on average. Yeah. Oh yeah, well that's just an example. But for example, another example might be the least square sample variance estimator is also unbiased, but the maximum likelihood sample variance is not unbiased. However, both are consistent. But we didn't talk about consistency yet. We're going to come to that.
Would an alternate definition be that the errors have equal likelihood of being positive or negative? Yeah, you're not reducing the system.
No, I don't want to buy that. I don't buy that. I don't like the sound of that at all. Because suppose that the distribution is asymmetric. Then we got a problem right away. Somebody was trying to foist off efficiency as a definition of unbiasedness a little while ago, and I said I didn't want to hear anything more about variance. So he is wrong. Said, you pronounce your name for me. So tell me what we mean by efficiency. Give me some examples of measures of central tendency. Okay. So those are all measures of central tendency. And we can use any one of those three to estimate the population mean, correct? Which one of those three is the efficient estimation? Because the smallest variance in the class of is the sample mean a linear or nonlinear estimator? It's linear. Is the median a linear estimator? It's not a polynomial or anything else. That's linear, right? Is the mode a linear estimator? Yeah. Is the median an unbiased estimator of the mean? Of the population? Yeah. Is the mode? In some circumstances, yeah. But not for an asymmetric distribution. The mode is not an asymmetric. So we have two estimators that are linear and unbiased regardless of the distribution. So how do we choose which one to use? You just told me. The sample mean. Right. in the class of, but efficiency is the definition of the best estimator. So my question is, so Hone and I have been talking about bicycles lately. And so I told him the other day, I'm a 5-time national champion. Does that mean that I have to race against Lance Armstrong? You know who Lance Armstrong is? So do I race against Lance Armstrong? No, I don't think so. I race in a class of dinosaurs and fossils. Okay, so that's a different class. That means that we've decided on beforehand how competitive, or the basis on which the competition is going to be run. Right? So I asked you some leading questions. I first asked you, what are some measures of central tendency? And we told you the mean, median, and the mode. And then we decided that the mean and median were both linear estimators. And we also decided they were both unbiased. And then I asked you, how did you choose between them? So the smallest variance. And so efficiency means not just that it has the smallest variance, but it has the smallest variance within the specific class. So if an estimator is efficient, then it means that in a certain class, it has the smallest variance. If we expand the class to include nonlinear estimators, are there other estimators that have smaller variance than the sample mean? Or let me give you a better example. Yeah, let's take that one. If we expand the class to include nonlinear estimators, are there better estimators than the sample mean and sample variance? The simple answer is yes. But you did pretty good so far. I know it wasn't until I got you on the last one that I was selected. So I'll ask that question to you. What do you say? If we broaden the class to include all unbiased estimators, linear and nonlinear, are there more efficient estimators than the least squares mean and the least squares sample variance? It's a hard question. It's a fact-based question. Maybe something we never talked about. Did you have statistics as an undergraduate student? Did you talk about the Gauss-Markov theorem? No? That's right then. I'll have to ask a different question. And the answer is that, yeah, if we broaden the class of estimators somewhat, then there are more efficient estimators, namely the maximum likelihood estimators. The maximum likelihood estimators have the property that their variance is all achieved at Cramer-Rao lower bound. The Cramer-Rao lower bound is given to us by looking at the Hessian of the joint density over the whole sample. And those are the minimum attainable variances of any estimator. So Cramer is the one who proves that if you include all unbiased estimators, then the maximum likelihood estimators are attaining the Cramer-Rao lower bound.
That means that for running a regression based on the other estimators, get a better estimate than the least squares?
As it happens, the least squares estimators are the mean. The sample mean is algebraically equivalent to the maximum likelihood estimator. So that is the most efficient amongst linear and nonlinear as well. It turns out, probably you saw this somewhere along the line, that if you construct the sample variance, the least squares estimator for the sample variance is S squared is equal to the sum of the xi minus x bar squared over n minus 1. We talked about that a week or two ago, I guess. And so we'll put an LS on that for least squares. So we're trying to minimize the sum of squared errors between our estimator and the truth. That's the estimator that we'll come up with.